Okay, so let me just come on the first iteration. It is not giving any output. So basically what is happening, if this input power is minus 10 dBm, okay, then basically there are some losses in this channel due to the optical fiber, and there may be some another insertion or connection losses. So at the receiver, basically the receiver is not getting the minimum required power to detect the signal. Okay, we can say the receiver is getting the less power than the receiver sensitivity, so it will not detect it properly, or it will it will not give any output, or it may give the noise. Okay, or BER it may be higher than the required one. So if I'm increasing this input power, so now if you just see, I'm inserting minus 6 dBm, something minus 6.84 dBm of input power, then basically we are getting some signal at the output, but the Q factor for that signal is not proper. It is 3.36, or minimum BER that is 0.00038. So this bit error rate is much higher. Okay, so for a communication system, the standard, I think the standard BER values are from 1 cross 10 to the power minus 9 to 1 cross 10 to the power minus 12. Basically, for any communication system, these values are preferred for the BER. So it depends on the transmission quality or the mutual agreement that is undertaken by the service provider and the receiver, okay, or the one who is taking the services. So if someone wants the better services, then it may do some mutual agreement for 1 cross 10 to the power minus 12, or 1 cross 10 to the power minus 9 is also fine. So what does it mean, 1 cross 10 to the power minus 9? So it means if we are transmitting 10 to the power 9 bits, then only 1 bit in error may be accepted. If we are transmitting 10 to the power 12 bits, then only 1 bit in error may be accepted. So this kind of error rate is preferred. And what is happening in this case, we are transmitting 10 to the power 3 or 4 bits, then 1 bit of error is getting, so that is not acceptable. Okay, so if we are increasing this input power, then basically we are getting some close values. Okay, so if this CW laser power is minus 2.89 dBm, then we are getting the maximum Q factor, that is 5.88, or BER that is 1.94 into 10 to the power minus 9. So what does it mean if we are transmitting 10 to the power 9 bits? Then basically we are getting 2 bits in error still. Okay, so if I increase further this input power, then what is happening? So the Q factor is 6.31, and minimum BER now it is 1.33 into 10 to the power minus 9. It means 10 to the power 10 bits are transmitting, and we are getting 2 bits or more than 1 bit in error. So that is acceptable. Okay, so if we are increasing this, then we are getting the improvement in the received signal. Okay, but so basically I have just simulated this from minus 10 dBm to 5 dBm. So if we increase this input power further, so like 6 dBm, 7 dBm, 10 dBm, or 15 dBm in positive, then basically the nonlinear effects will come into the picture. So almost 5, 6, or 7 dBm, up to 5, 6, or 7 dBm input powers are preferred to avoid the nonlinear effect. Okay, so if we just see around 1.05 dBm of input power, okay, so we are getting Q factor that is 7.51, and if I just consider this as minus 1.31, or let's say, yes, this one, so minus 2.10, or let us just consider minus 2 dBm of input power, then we are getting the Q factor close to 6. Okay, so now what happens if we just decrease the transmission rate? Okay, so this link is operating at 10 Gbps. If I operate this link at 2.5 Gbps, then what happens? So I designed some another link. So we just see in this case, this layout rate is 2.5 10 to the power 9. From here, this data rate is basically 2.5 into 10 to the power 9. Okay, so if I just operate this link for the same input powers, so if I spread this from minus 10 to 5, so I'm again calculating all CP iterations in the active layout. So this is for 2.5 Gbps. So are you designing this link? Yes, please. Okay, so for the 10 Gbps, when the link was operating at 10 Gbps, then basically for minus 10 dBm of input power, you are getting nothing at the output. But now in this case, we are getting some signal. Okay, although the Q factor is not as required, but now if I increase the input power, then basically we are getting some proper I diagram or Q factor. Okay, so now in this case, basically minus 8.42 dBm of input power is required. Okay, but earlier, or if this link is operating at 10 Gbps, then approximately minus 2 dBm of input power is required. It means we need to transmit additional 6 dB of power if we are switching the link speed from 2.5 Gbps to 10 Gbps. So basically, I've just given you this idea because the next lecture that will again be taken by me, that is on energy efficient optical access networks. So my idea here is that if we are transmitting data at 10 Gbps, then it will consume the higher power, and if we are transmitting the data at lower rate, then it will consume the low power. Or at the transmitter side, we need to require to send the less amount of power. Okay, so you will have this idea there also. Okay, so now we'll check the receiver sensitivity also. Okay, so what is the minimum power at the transmitter which is required for getting, let's say, the factor 6 or minimum log of BER, that is 10 to the power minus 9. So we want to optimize. So first we will optimize the input power. Then we will see what is the power difference that is required at the photo detector, or we can say suppose the link is operating at 2.5 Gbps. So what is the power, additional power that is required at the detector to get the same BR performance 10 Gbps? So that is the power penalty due to the higher speed. And similarly, we can say if we are having the single mode fiber of 80 kilometer, so what is the power penalty due to this 80 kilometer fiber? So in that case, we'll Just see the receiver sensitivity for the back-to-back case and the receiver sensitivity for the 80 kilometer fiber. Okay, so now we want to optimize this. Okay, so I will try to optimize this in such a way that we'll get the Q factor here, that is 6, and minimum log of BER, that is 1 into 10 power minus 9. Okay, so have you installed this software? You are doing simultaneously, or please let me know. Yes, please. Okay, so basically for optimization process, we must have some idea about the approximate values in which range basically we'll get the Q factor 6. For example, suppose this Q factor 6.3, that is at minus 8.42. Okay, so we are providing the input power that is approximately minus 8 or minus 9, then we may get the Q factor 6.3. So one process here, simply, that is not basically, I'll say the optimization, but it is the 10 trial method. So what you can do, so you can spread this input power in some close range. Okay, so let us just say from minus 10 to minus 8 dBm. Okay, so now I'll run this again. So basically what we are doing, we are just following the hit and trial method, or we are just entering some rough values, and then we are trying to get the Q factor, that is 6, or the BER, that is 1 plus 10 to the power minus 9. Okay, so now let us check. Yes, so now the difference between the input power values is now reduced, so we may get Q factor 6 at some particular value. Okay, so if you just consider this minus 8.63, here we are getting the Q factor, that is 6.01, or the BER, that is 9 into 10 to the power minus 10, or we can say 1 into 10 to the power minus 9 approximate value. Okay, so we get the approximate value definitely, but now we want to do this by optimization process that is available in the software. So now how we will do it? Okay, so we have the idea about this approximate value, that is minus 8.63. Okay, so now I'm just reducing one iterations. We don't require the multiple iterations for the optimization process because it will automatically optimize. Yes, so now we need to click on this optimization process. Okay, so here we have the single parameter optimization. So now our optimization type is goal attaining. Basically, we want the Q factor to be 6. Okay, and then suppose similarly we want to maximize something or we want to minimize something, then we have the different kind of optimization. So now in this case, we want the Q factor to be 6, or the minimum BER, that is 1 cross 10 to the power minus 9. Okay, so now result tolerance, so let's say I'm just curious about this tolerance. So in this case, it is 0.01, let's say, and the maximum number of passes, that is 50. So if in 50 trials or runs, if it is attaining the goal, then it is fine, otherwise it will stop. Okay, so now parameter. So which parameter we want to optimize? Yes, so what is the parameter right now? Here we are optimizing. So we are optimizing the input power, right, of CW laser. We'll click on this CW laser, and now we'll click on this power. Okay, and then click on this. So now we want to put some rough values in which this Q factor will be 6. So let's say if I am just putting the value that is minus 15 to 10, okay, and we know that in this range we will not get the Q factor 6. But let's say what happens in this case. Okay, then we'll optimize it again for some values. So now we want to click on the result, and then basically the what parameter of result we want to optimize, or we want to optimize for. So we are optimizing it for the Q factor and the BER. So these are the parameters of the BER analyzer. So then we'll go to this BER analyzer. So in this case, we have the maximum Q factor or minimum log of BER. So we can optimize from any. So let's say minimum log of BER. So minimum log of BER. So for what value we want to optimize? We want to optimize it for minimum log of BER. So that is 1 cross 10 to the power minus 9. So here it is log. So that's why minus 9. Okay, or we can have the maximum Q factor, that if we select this maximum Q factor, then we'll put here 6. Okay, so now I'll try to click on generate, then okay. So now we have put some values for the optimization. So now we need to run the optimization. So now click on this, run all optimizations, right? So now I'm performing this. So let's say what is happening at the optimization. So first it will run for minus 15, then minus 10, then it will take the average, so minus 12.5, then some new values. So basically it started from minus 15, and then it checked at minus 15 we are not getting, then it checked some on other values. So at minus 10 dVm we are getting some close value for the BER, but it is not as desirable. We are not getting as it is desired. So it will run for the maximum passes 50 times. Okay. So still it is running. Yes. So now it is completed. So now I'll click here. So now if we check, so basically we are not getting the desired output. Okay, for what we are interested, that is the Q factor 6 or the minimum BER, that is 1 cross 10 to the power minus 9. Okay, why it is not happening? Because we are not having the idea about the approximate or rough values of CW laser. Okay, now if we see here, so now you see here it is now optimized. Okay, earlier we have 3 options like normal, sweep or script. Now it is optimized. Okay, but this is not as optimized as we are requiring. So basically we need to do some changes in this. So again, what we are doing, so we need to put some correct values here. Okay, so let's correct value is minus 8 to, sorry, minus 10 to minus 8. And again here the minimum log of BER, that is minus 9. So again, let's perform the optimization process and check what happens. So now if you see at minus 10 we are getting the minimum log of BER minus 5, and minus 8 we are getting minus 11. So we will have some input power of CW laser in this range. Okay, so now it will run successfully, or it will optimize successfully. So in very few iterations or passes. So basically, if you just see four, I think 9 or 10 passes, we have optimized this link. So now if I see, okay, so that is 5.9989 Q factor. Okay, so tolerance is 0.0001. So if I just put there 0 or 0.000001, something like this, then we'll have almost Q factor 6. And this 9.91 into 10 to the power minus 10, that we can say as 0.99 into 10 to the power minus 9. Okay, so this is very approximate value. So for this input power, that is minus 8.64 dBm, we will get the Q factor 6. Okay, or let me just try to optimize by Q factor. I've already given you idea about the BER. So let's say we want to optimize this from this maximum Q factor. Okay, so now we need to put here 6. And suppose if someone agreed for Q factor 7 or 8, then we need to optimize it accordingly. Yes, so now it is running for the Q factor, right? Yes, so minus 8.64. Again, we are getting minus 5.9989. So that is very similar to the optimized values of input power for log of BER, minus 9. Okay, so this minus 8.64 dBm will give the Q factor 6 or minimum log of BER minus 9. So now we will just check what is the receiver sensitivity. So for this link or for this receiver, so the receiver sensitivity is minus 27.922 dBm. Okay, so this much of power is required at the receiver to get the 10 to the power minus 9 log of BER. Okay, so now what happens, or how much is the power that is required if we increase this data rate to 10? Okay, so we have the separate link, or let us just do in this only. So I'm just changing this 10. So now we'll have this as 10 Gbps, right? Okay. So if I run, so basically we need to delete the optimization first because it is optimized. Okay. So I'll go on this optimization, and now I've just deleted this. So we have already checked if this link is operating at 10 Gbps, then approximately minus 2, I think minus 2 or minus 1 dBm of power was required, right? We must have some idea, or at least we should add the range in so that the optimized value will come within that range. Okay, so now I'll just optimize this. So it is again 0.001, and then so we want to optimize the CW laser parameter power. So now let me just add some rough values, minus 8 to 10 dBm. Okay, now in this case the range is somewhat large, but it will not be a problem, it will optimize. Okay, so now we need to move to the results. So in the result section, we want to optimize it for minimum log of BER. Sorry. let's say maximum Q factor. So it is 6. Okay, so now I'm running the optimization. So you just check how it is moving towards the close value. Okay, so now in this case, the CW laser is minus 2.69 dBm, and for that power we are getting the Q factor that is 5.9991, that is very close to 6. Okay, so Q factor is 5.99, or we can say the minimum log of VIR, that is 9.9 into 10 to the power minus 10, or 0.99 into 10 to the power minus 9. Okay, so now again we'll check how much is the power that is required at the receiver. Sorry. Okay, so in this case it is minus 21.978 dBm. Okay, so almost 6 dB more power is required at the receiver. So we can say the receiver, the power penalty due to the higher data rate, that is moving from 2.5 to 10 Gbps. So there is a power penalty of 6 dB. Okay, we can say if we are not transmitting some higher powers, then receiver will not able to get the proper value, the value well above the receiver sensitivity levels, so it will give the noise. And if we are getting the power at the receiver that is above the receiver, good results. Okay, so 6 dB. So basically, suppose if some optical link is laid out in the field, okay, then basically we need to do the power budget analysis. So in this case also, if you just see here, so how much is the power budget then that we can have for this link? So suppose we are transmitting the data at different speeds or different links, then basically we need to have some safety margin also, so that the link may perform well at the higher speeds also. So suppose if one is operating at the lower data rates, then we may decrease the transmitted power to save the power. Yes, so now we want to check, we want to perform the same process for the length. Okay, so now we want to optimize the fiber length, for which we'll get the Q factor 6, and then we'll check what is the power penalty due to this optical fiber. Okay. So now I'm just making this as normal. Okay, and let's say here I'm having 0 dBm of power. Okay, so now I want to optimize this length basically. Okay, so let us just have one iteration here. So let's check what happens if 0 dBm power is applied for the 80 kilometer fiber length, and when the link is operating at 10 Gbps. Yes, so it's over. Yes, we are getting Q factor that is 7.19, and the minimum BR that is 3 into 10 to the power minus 13. So basically, we have already calculated it is approximately minus 2 something for getting the BER level same. Okay, so now I want to optimize this fiber length. So for what length I'll get the Q factor 6? So I'll again just click on the optimization. Sorry. Single parameter optimization, then goal attaining. So let's say 0.001. Then now the parameter is the fiber length. So it will come under this single mode fiber, then length. So now what is the range, or what will be the range for which the Q factor will come 6? So suppose we have some fixed parameter, that is the data rate is fixed, and we are also fixing some transmitter power. Then we are just checking up to what fiber length we can transmit by this link, up to what maximum length we can go. Okay, so I'm just putting from 80 to 90, because at 80 it is giving the Q factor that is greater than 6, something like 7. Okay, so definitely for Q factor 6 we'll have some more length. So I'm just roughly entering this value from 80 to 90. It may come under this or it may not come, I don't know. We'll just check. So if I click here, then BER analyzer, then minimum log of BER, so it is -9. So now I'm just running all the optimization. Yes, it will definitely come in this range, around 85 kilometer of length. Yes, so for 85.68 kilometer, we are getting the BER that is 1 cross 10 to the power -9. Okay, so it is 5.997, or it is 9.99 into 10 to the power -10. So it is approximately 1 cross 10 to the power -9. Okay, so now we just see here. So now it is optimized. Okay, so fiber length is 85.68 kilometer. 85.68 kilometers. So with these parameters, we can transmit satisfactorily for 85.68 kilometer length. Okay, so now what is the minimum receiver power that is required at the receiver? So that is minus 20.418 dVm. Okay, so that is for 85.68 kilometer length. Okay, so if we have the fiber length that is 85.68 kilometer, then there must be some nonlinear effects that is occurring inside the optical fiber. Definitely the nonlinear effects affect much in the WDM or DWDM systems, as there are closely spaced signals that are transmitted within the channel. So there is more self-phase modulation, cross modulation, or we can say the four-way mixing, etc. But in this case, very few effects are there, so the power penalty must be semi-small. So now we want to check the power penalty that is occurring due to this single mode optical fiber. Okay, so now what we need to do? Good, we need to basically remove this fiber. Then only we can say, suppose we have fiber, then we are having some nonlinear effects due to this optical fiber. So when we will not have these effects, when we are directly connecting the transmitter to the receiver. Okay, so now what I'm doing, I'm just removing this single mode optical fiber. I'm directly connecting it. So now basically we want to check the power penalty in this link due to the single mode fiber. Okay, so now, and I'm not interested to change this power also, because if we suppose decrease this power, then again, suppose at less powers the nonlinear effects will be less, and at high power the effects will be high. So basically I'm transmitting 0 dBm power from here. Okay, so now what I can do, I'll just put some passive component here. So that is basically the attenuator. So I'm just going to the passive library, then optical. So here you have some attenuator library, right? So now let us place one optical attenuator. Yes. So now I will optimize this attenuation level in such a way to get the Q factor 6. Okay, but really I don't have idea for what value will get the Q factor 6. So let me just run this at this point. So I'm getting here, sorry, there is some problem, I think. That is already optimized. Okay, so we need to delete this optimization. Yes, now it will run. Okay, and we need to uncheck this also. Yes, so now in this case, this Q factor is 349, or the minimum log of BER is 0. 0 means basically someone is asking questions from 2 days. So like we are getting the minimum log of BER, that is 10 to the power minus 95 or minus 99 or minus 100. So this is some kind of same situation. Okay, 1 cross 10 to the power minus 99 or minus 95, it is approximately 0, very less. Okay, so that is the same situation. Okay, so now basically I need to add some values, but I don't have really idea. Okay, so either what we can do, so let us directly optimize this, okay, without having the idea. So 0.001, then now what parameter we want to optimize? The attenuation level of the optical attenuator. So attenuation here. So I don't know the value, but I can put some large range. Okay, so let 0 to minus 20, and then Q factor. So minimum log of BER, let me just select this one, minus 9. Okay, if I just optimize this, so I hope this will come in this range. No, it will not come. So we further need to increase this attenuation level to get the BER in the desired range. It is still running. Yes, now it is over. So still we are getting the Q factor, that is 8.5, and minimum log of BER, that is 8.6 into 10 to the power minus 18. So we need to further increase this attenuation range, I'll optimize it again. Okay, so that's why we must have some rough idea. The properties, parameter, attenuation. So now let me have 0 to 25, or it is better if I have it from 20 to 25, because at 20 we have already optimized. It is not coming in this range, so it is not a problem. Yes, so this range is fine. Okay. Now I'm optimizing. Sorry. Yes. Now we'll get definitely. Yes, so optimized. Yes, we are getting 5.99. Okay. So now let us just check what is the receiver sensitivity. So what is that is required at the receiver? Sorry, not this one. It's not connected. Yes, so now in this case it is minus 24.86 dBm. Okay, and earlier it was minus 20.418, and that is due to the 85.68 kilometer fiber length. Okay, so we just take the difference of these two receiver values. So when there is a optical fiber of 85 or 86 kilometer length, then receiver must require at least minus 20.418 dBm of power. Sorry, minus 20.418 dBm of power to give PQ factor 6. And if we are not having any fiber, okay, I'm just directly verifying this link for back-to-back condition. Okay, so you must have seen various papers. So those papers compared the results with the back-to-back, and due to some effects occurring inside the fiber. And here I am giving you the idea with the whole effects coming inside the fiber, not individual results. Okay, so due to this 85 kilometers, basically we require additional approximately 4.4 dB of power. So suppose for 80 kilometer, the power penalty is approximately 4 to 4.5 dB. And if we are just transmitting the data for the 20 kilometer link, then this power penalty will be somewhat less, and it will be approximately 1 or 1.5, and depending on other parameters also. So at what data rate we are transmitting, or what are the effects that are occurring inside the system. Is it clear to all? Yes, so in this case, basically up to now you have just checked, you are aware about how to check the receiver sensitivity, how to optimize different parameters for getting some different desired results. So in this case, we have optimized the power, also the fiber length, and similarly you can optimize other parameters also for getting the Q factor or BER some particular value. So in our case, we optimized it for the Q factor 6 or the quality factor, sorry, the minimum BER, that is 10 to the power minus 9. Okay, so we can similarly optimize it for 1 plus 10 to the power minus 12 or minus 11, depending on what performance we want to give at the receiver. So suppose some internet service provider company is laying down the separate link, or in the already deployed network, it is setting up or extending some new links, new connections. So depending on the receivers or the person who is taking the services, depending on his quality of what he or she want to take, so we can design it accordingly. Okay, so now in this, up to now we have given the idea about the simple link. So now I'll give you just some idea about the WDM systems. Then you must have already some idea about the WDMs, and Mr. Amandeep gave you some idea about the WDM systems. So now I'll just give you how to multiplex and demultiplex various signals with the help of AWG, Arrayed Waveguide Grating. AW is really a very good component, optical component, passive component basically, so which is used for switching, networking, the optical links. So let me just open the another browser. Yes. So is my link, this new link is visible to you? I don't know, or I need to share it again.
Yes, sir, it is visible now.
Yes, participant.
It is visible now,
now
sir.
What is visible?
Visible, sir.
It is WDM 8
yeah.
8 yes, sir.
Yes. Yeah. Okay, so this is normal WDM link. Okay, so what I have done in this link, I've just taken the WDM multiplex. So it is 8x1 multiplexer. Okay, WDM mux 8x1. Okay, so we have different channels, or we can say we have some filter in this WDM mux. So the port 1 is for 193.1, port 2 is for 193.2 terahertz, and similarly the port 8 is for 193.8 terahertz. Right. So we are having the WDM mux, which is multiplexing the wavelengths that are coming in the range from 193.1 terahertz to 193.8 terahertz. Okay. So now what I have done, simply basically you have the idea about this link. Okay. So I have just taken 3 cases, and in these 3 different cases I have transmitted at different data rates. So if we just check this layout data rate, the bit rate, that is 10 GB. Okay. So from the first transmitter, basically this whole module, the 4 components, CW laser, PRVS generator, NRZ pulse generator, and Mach generator modulator. This is the combination of the transmitter. Okay, whole package. And let me just give you, this combined package is also available in this Opti system. So if I just move to the transmitter library, then optical source, sorry, optical transmitter. Yeah. So basically in optical source, we have different sources. Okay. And if we just go to this optical transmitter, then we have the WDM transmitter. Okay. So we can use this, we are multiplexing, or if we are transmitting the multiple transmitters or wavelengths, sorry. And if we want to have separate, then this is the optical transmitter. Okay. So in this case, you can see we have the PRVS also, we have the NRZ also. So, and we have all these parameters. Okay. So this one component is sufficient to replace all these 4 components. Okay. So now from the transmitter 1, I am transmitting the signal at 193.1 terahertz, as you can clearly see. From the transmitter 2, I am transmitting at 193.2. Similarly, from transmitter 3, 193.3, and so on. Okay. So now what is my intention? So from this transmitter 1, or we say at wavelength 193.1, we are transmitting at 10 Gbps, right? And I'm transmitting from this second transmitter, that is 193.2 terahertz. That is, if you just see, sorry, 4 Gbps. Let me just check. Okay, I'll check. And from this transmitter, I've transmitted at 40 Gbps. Okay, so what we can do, so actually bit rate that is taking from the main layout, and if I just put into 4, then basically it will multiply. So 10 into 4, so 40 Gbps data we are transmitting here. Okay, so let me just confirm at what rate actually I'm transmitting from the transmitter 2. Yes, so I think it is at 4 GB. Sorry. Yes, 4 Gbps. Okay, no problem. Let us just check. Or it is better if I just say 5 Gbps. Okay, rather than 4 Gbps. So now we need to go to transmitter 2. Yes. So now in this case, I've taken the 20 kilometer fiber. If I take the length of fiber like 80 or 85 or 90 kilometer, then basically in this case, the performance will be very bad, as we are transmitting the multiple signals. So the non-linear effects will be much higher. Okay, so let me just simulate this. So there is no iteration, only one iteration here. Yes, it is now simulated. Okay, so from here I'm transmitting signals. So let me just check the spectrum here. Okay, and here, if I just maximize this. Okay, so let me further zoom it out. So this signal is 193.1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm transmitting the 8 signals. So this is the structure at the transmitter side or at the central office, or you can say at the OLT, optical terminal. Okay, so this is the complete part of the OLT or central office. Okay, so now we are transmitting it through the optical fiber. Then what happens to the another end of the fiber? You can clearly see. So actually we have transmitted only 8 signals. Okay, but we are getting various signals. So this is nothing but the spurious generation of the other frequencies, that is due to the 4 mixing. Okay, so but we can't ignore. Okay, so you can see here it is 193. So if you just observe, so we are getting much higher amplitude of the signals which are transmitted from the transmitter. So 193.1, 2, 3, 4, 5, 6, 7, 8. Okay, and if we just see the other signals, so those signals are getting very less amplitude or magnitude. Okay, so the receiver will not basically give some proper result from these spurious signals, but definitely it will degrade the performance. Okay, so what we can do for this, I'll not go into the detail for that. So we can use the FBG filters or some other filters to separate out these wavelengths. Okay, so we can have the filter at 193.1 or 193.2, 3 or up to 8. So that will filter out some particular frequency. Okay, so now this WDM demux, so we have the channels. Okay, so again we have the filters here. Okay, so it will separate out 193.1 wavelength, 193.2, 3, 4 up to 8 wavelengths. So if I just check this point, so I'm getting here one wavelength and components will be there. Okay, so similarly at port 2, this is connected to port 3, right? Yes. So here I'll get 193.3. So let me zoom it out and check what is the wavelength. Yes, so it is 193.3, right? And similarly at port 2, so let me check the spectrum analyzer of, yes, I think it is. So it is 193.2. Okay, so at 193.1, I am modulating the signal at 10 Gbps. At 193.2, I'm modulating the signal at 5 Gbps. And at 193.3, I'm modulating the signal at 40 Gbps. Okay, so let me check the performance. So it is the beauty of the WDM systems that we can transmit the data at different data rates. Okay, and in this case, basically we have 8 users. So one transmitter is dedicated for one particular user, or you can say the optical networking unit, ONU. Okay, so depending on the service requirement, how much cost the receiver is going to pay, or at what data rate he or she is willing to have the services, so we can transmit. So if we just check here, so at 10 Gbps, the Q factor is 4 and the BER is 1 into 10 to the power minus 6. Okay, it is not good. So what need to be done? So either some amplifier need to be placed, or some more power from the transmitter needs to be transmitted. Okay, now what happens in this case? So if I'm transmitting the data at 2.5 Gbps rather than 10 Gbps, then I'm getting very good Q factor, a very good signal at the receiver. I can say the height is also very good, and the minimum log of BER, that is also very good. Okay, so in this case we can transmit less power from the transmitter. I am here just giving you some idea how to design the different links. Okay, now this link is at 40 Gbps, definitely will get anything, because 40 Gbps is too much high, so we need to worry about this. So I have also not checked here, but we need to use the optical amplifiers or regenerators. Definitely at receiver side we use the regenerator. Okay, but that is for the electrical signal. Sorry, yes, electrical signal. Okay, but we need to place some inline amplifiers also for this particular link. Okay, or simultaneously we need to transmit some much power from here 0 dBm to, let's say, okay, let me just check what happens at 10 dBm. I don't know, I'm just trying it. Let's check whether we are getting something or not. We are still not getting, so we need to amplify the signal at the intermediate levels. Okay, so this is basically from the WDM mux or demux. Okay, now we can do the same operation by using the arid waveguide dating. Okay, so here I have taken this initial part from this layout. I'm just trying to demultiplex it from the AWG. Okay, so we have the multiplexer library. So here we have AWG. Okay, so this is n cross n AWG. So here the size of this AWG is 8. Okay, and the center frequency of this AWG is 193.1 terahertz and frequency spacing is 100 gigahertz. Okay, those parameters are important. So now if you just check here, sorry, I need to run this. Yes. Okay, so I'm getting 8 signals here, right? 193.1, 2, 3, 4, 5, 7, 8. So those signals are 100 gigahertz spaced apart, right? So that's why if we are just putting the frequency spacing at this point 100 gigahertz, it means the spacing between from this port to this port and this port to this port, that is 100 gigahertz. Okay, and from this port to this port, basically for these two consecutive output ports, that is 100 gigahertz. Okay, so now what will happen, as actually we are just providing all these input wavelengths to port 1. Okay, and the other ports are grounded or basically optical null. If we just keep this unconnected, then it will give the 0. Okay, so we need to connect, definitely we need to connect it from the optical null. Okay, so now all 8 wavelengths are coming at this port, and as the center frequency of this AWG is 193.1, it means 193.1 wavelength will come at this point, and as the frequency spacing of this AWG is 100 gigahertz and two consecutive input signals are 100 gigahertz space apart, so 193.2 wavelengths will come at this port, 193.3 will come at this port, 193.4 will come at this port, and so on. Okay, so let me check here what frequency we are getting. So it is 193.1. Similarly, if we just check this fourth port, so it must be 193.4. Okay, here it is in nanometer, so I'm just converting it into the hertz. So it is 193.4. Okay, so this is some kind of demultiplexing with the help of AWG. So now actually in this case we have 8 wavelengths, and we have this 8 cross 8 AWG. Okay, so now let me just reducing the size of this AWG. Okay, so now there are only 4 ports. Okay, so what will happen now? So let me just give you some idea. So 8 wavelengths, 193.1, 2, 3, 4, 5, 6, 7, 8 terahertz are coming here. So as the frequency spacing is 193.1, so at this point we'll get 193.1, here 2, 3, 4, and now again it has the cyclic property, so it will start repeating its ports. So 5, 6, 7, 8, something like this. So let us just check. So 2 wavelengths must be there, 193.1 and 193.5. Let us just check. So 193.1, 193.5. Here 193.2, 193.6, and so on. Okay, so now I want to use this as multiplexer. Okay, here I've just given you the idea how to use this AWG as demux. Now I will just try to multiplex these signals help of. Okay, so I think automatically these are connected, but whether it is connected right or wrong, I don't know. Let me check. 2, 3. I think it is correct. Okay, so now 193.1 again is the center frequency. Okay, and here we are having 193.1, so it will come at this point. And let me just connect the spectrum analyzer and run it. So now 8 wavelengths are now multiplexed at port 1. We have applied the signals at different port 1, 2, 3, 4, 5, 6, 7, 8. But we are getting all these signals multiplexed and combined at port 1. So I'm getting 193.1, 2, 3, 4, 5, 6, 7, 8, something like this. Okay. So why so it is happening? So basically here 193.1. So first frequency will come at this point. So now again the wavelength spacing is 100 gigahertz. Okay. So here it is minus, and let us check if it is plus. So basically minus or plus will not affect, but it will affect the sequence only. I will not go much deeper. Sorry, some problem. But you just go through this AWG component and then check. Okay, so let us just consider this as 100 minus 100. Okay, so you go through this AWG, then you'll get this concept also. It's not a big problem. I don't know what problem happened, but okay, now if this is connected to this point, okay, so now it is the multiplexer and it is the demultiplexer. Okay, so AWG is performing this operation. So here we are getting two 193.1 and 193.4. Sorry, 5 years. So, but now I think SRS effect is there, I think.
So center frequency has to be changed, which is
Okay,
already
yes. Yeah,
193.8. Yes, sir.
Yeah. Yes, thank you. Yes.
Okay, sir.
Now it is fine. Yes, thank you. So again, here we are getting two wavelengths. Here 193.4 and 8, I think. Let us just check 4 and 8. Okay. So by using this passive component AWG, we can add some flexibility in the network. And I think you'll have a very good idea about this kind of architectures in the next lecture that will again taken by me. So now I'm stopping at this point, and now I'm open to the queries from the participants. Yes, please. And I tried to give you something new, but few of you might already aware about these things as you are actively working in the optical networks. Yeah, please.
Okay, sir. So first of all, I would like to thank on behalf of all our participant, Amit sir. You have already given a very good insight about this particular software and all that thing. Basically, when we are starting also things like we are just starting from the scratch, and also the way by which, sir, you have tried to explain all that thing. Many of our participant may have got very good. What you can say that insight as well as the insight as well as the inspiration from this work, and definitely, sir, we will just try to what you can say that implement this type of thing in whatever the domain which we are working and all. So thank you very much, sir, once again from all of us. Thank you.
Yes, thank you, and welcome for your very kind and motivational words.
Thank you, sir.
Yes, and one thing I would like to tell to all the participants. So actually, I recently worked on these optical networks towards my PhD work. So I worked on the energy efficient optical access networks, and also tried to design some latency awareness in the optical networks. Okay, direct intervenue communication techniques. So if someone of you are working in this area, or suppose someone of you are designing some links, and if you want some help, then I'm already open. Okay, so you can definitely mail me or just call me. You have my number, you have my mail ID. So I will try to help you out with maximum possible way. And there may be some delay, 1 or 2 day delay, as due to the working schedule, busy working schedule, but I will try. Okay, and there may be some case that I will not be in a position to help you out for all queries, because I am also not a very much expert, but basically as the teaching and learning process, we can try. Yes. Yes, thank you all. Any other
Hello, sir.
questions? Yeah.
Yes, sir. Amit sir. Hello, sir.
Yeah.
Good morning, sir.
Good morning.
Hello.
Yes, good morning, Rajat.
Sir, thank you very much for this nice. Actually, sir, yes, sir. Can you hear me, sir?
Yes, definitely. Yeah.
Sir, can you hear me?
Yes, I am hearing you.
Sir,
Yeah.
sir, actually, I just want to know whether, as a research point of view, just I need to know that is this simulation work is sufficient, and what you are doing particularly for this validation part, because this is just a simulation part, and we can't proceed particularly on these simulations for research work. So
And
for the
yes.
validation, what we can do, sir? Actually,
So, Rajat, can you please tell me in which university you are working?
Sir, I am working in Mumbai University, and I am a research scholar at NIT Gujarat.
Okay, okay. So basically,
And sir, actually, I have some simulation in the direction of polarization mode dispersion, sir. I just send you the paper. Actually, I was finding difficulty in the modulation format, 64 QAM, and so I can't able to do that part in the simulation also. So that I will mail you the sir paper where I was finding the difficulty. But sir, can you just suggest me what I can do for validation part?
Actually, I'd like to say that in India, particularly, okay, so we have very less experimental facilities. Okay, as of
Yes,
now,
yes,
I think in IIT Delhi, Mumbai, or I think in IIT Madras, we have some good research facilities. So I think you can approach there. In IIT Delhi, I think actually I'm not remembering the name. Abhishek, I think Dr. Abhishek got.
Actually, I have mailed to Abhishek sir also, but I actually 2-3 mails I have sent in IIT Madras also I have sent, because they have done
in IIT
some.
Madras, Deepa Venkatesh ma'am is working on this field. Deepa Venkatesh.
Okay.
Yes, and in IIT Kharagpur, Dr. Gautam Das is working, but as you know, these people are having very busy schedule, so they may respond, they may not respond.
Because sir, actually, sir, I have contacted them, but I didn't get any response. And even I have, sir, gone for ERNet. They have done some VLC link on hardware. VLC link in from IIT Madras only. So I was doing some. I was planning for some experimental work, sir. So
Yes,
I
but
just
experimental work is very limited, because actually here I just show you 40 Gbps transmission. Okay.
Yes,
but suppose in the laboratory we are having 2.5 or 5 Gbps.
Yes, sir.
It will take time to purchase 10 Gbps, upgrade to 10 Gbps. And suppose if someone has upgraded to 10 Gbps, then now the research at 10 Gbps is over, so it is coming on the 40 Gbps. So from where you will get these components. So basically, this is the problem. But I would like to suggest you. Yes, I would like to suggest you that if possible, then you can approach the. If you get the experimental facility, then it is good. Otherwise, what you can do, you do some theoretical modeling and then simulation modeling. So basically, there are two kind of work that is supporting the results. So then I think you'll have at least some good results, and you'll have, yeah.
Sir, for a small link, is it possible, like as I thought, because in this particular part it is difficult to do experimental work. So later on, we thought in that direction that let us start with some VLC link, indoor VLC link designing using hardware. So that will be a kind of experimental work, and in OptiSystem we can do particularly a kind of, because they have in this latest version they yes sir. In this version they have support designing of VLC. So the software part is supported from this, and hardware part we can do in the indoor systems or something like VLC link.
So basically, these are for very short distance. Okay, so you can go experimentally, but I think if you are designing the single mode fiber or these long links, basically, okay, then it will not support the results. Basically, if you are doing some work on FSO for short distance, and if you are doing on this SMF, then basically how you will match these results, I don't know. But
yes, yes, you see, yes, that's why, sir, actually, because yes, sir, because for small links it is possible to do experimental work with validation in the simulation, but for long link it is difficult to do experimental work. That's why, sir, I thought that it is if I start with the hardware part in the VLC, then actually I can support my software part along with the hardware in a short link.
Yes.
Okay, sir. Okay, sir. Okay, sir. Sir, I will mail you the paper where I find the difficulty. Hello. Yes, sir. Thank you, sir.
Okay, yes, you're welcome. Yes, anyone else? Okay, so thank you, and again we will meet at 12, another informative session. So I would request you all to attend that session. It will be very useful for you who are working in the optical access network and trying to design some flexible, energy efficient, cost efficient links. Okay, so thank you all. Yes.
Okay, sir. So can we leave now?
Yes.
Yes. Okay, sir. Thank you.